we are still discussing how to compute volumes of given solids. Now, last time I showed you a method which is called method of cross sections. Now here you see once more how this method works. So what we do in order to compute the volume of a solid, when using this method, we place the solid into our coordinate system. Now, if we assume that the solid lies between A and B, we are going to slice the solid by planes which are parallel to the x-axis. And what we essentially have to know is this area here, a to the x, so the so-called cross sections, area of the cross sections. Now, once we have identified, because identifying the area, this is a problem we have discussed previously, because it's an area problem. Here we are talking about volumes. So the first thing is you have to figure out, okay, how to compute the area of the cross sections. These already might involve integration. Now, once you know this function a of x, so which gives you for every position x the corresponding area, you can use this information in order to compute the volume. So last time we showed, okay, what you essentially do is you divide the interval AB into subintervals. You choose a sample point on every subinterval. This sample point is representing the base region of your cylinder. And then you look at the interval, for instance, xi minus 1 xi. You use the red region you see here as the base region of a cylinder, and the height is xi minus 1. So in other words, you approximate the volume of the given solid as the sum of the volumes of cylinders, which you compute instead. And then you make the subdivision smaller and smaller, and in the limit you get the integral. Now, since integral has the meaning of integral roughly is summing up things, so summing up very tiny small quantities. You can also look at the result or at the definition of the volume which we obtained by using this process as, okay, you sum up all the area of the cross sections, because by definition the volume is the integral from a to b, a of x dx. But you should keep in mind that we obtained this here, this definition. We didn't obtain immediately the integral. We first looked at the Riemann sum, and then we let n tend to infinity, and in the limit we get this integral here. But as I have explained to you, intuitively you can always think about the integral as something like summing up very small quantities. So here more or less you sum over all those areas a of x. So that's the way you compute the volume by using this method. And as I said, this method sometimes is called method. So this is one method to compute the volume of a given solid. Now, as I have explained to you, there is a need for finding another method, because there are certain solids whose volume we are not able to compute using this formula, or not able to compute easily using this formula. One example I showed you last time. So you have the function f of x is equal to 2x squared minus x to the cube. Okay, so if you have this function, if you plot the graph, you see that the function is 0 at 2. So I have many choices for the colors. And the function is 0 at 0, so what you get is something which might roughly look like this here. Okay, so you see that you have a region here, which is bounded by this function from above and bounded by the x-axis from below. And what we want to do is we want to rotate it about the y-axis. Okay. By doing so, we get this a solid, which we called last time solid of revolution, so a certain type of solid of revolution, and we want to find the volume of this solid of revolution. Now, but if you want to use this method, if you want to apply this method, so what you have to do first is you have to figure out, as I said, this function a of x. Now, in this case, okay, so you see that if you slice here the solid, okay, by planes which are like this here, then the cross sections are washers. So what you need in order to compute the volume at the area of the cross sections is outer and inner radius. So essentially, you have to compute this point here and this point, independence of a y. But this essentially means you have to solve this for x, which is not possible because, or it is possible but complicated, because this would give you a equation of third order. There is a method to solve it, but the resulting solutions are very complicated. But if you would be able to solve it, of course you can use this method immediately. But for instance, if you replace this polynomial by a polynomial of degree 5, then you maybe have heard that it's not possible to write down the solutions. So then this method would completely break down. So that's why we have discussed last time already another method, the second method, which has to be compared with the first method, is the so-called method of cylindrical shells. So last time I already explained roughly how this method works. So you see that you have given this function. This is different from the function I plotted here, but let's assume we have given this function here. Again, you want to rotate the function about the y-axis. You get the solid of revolution. The question is how to compute the volume of the solid of revolution. So what you get is the blue solid here. Now, the way we approximate the solids, for the new method, the way we approximate the solid is quite different. So we do not here, we slice it by planes which are parallel to the y-axis. But here we look at things completely different. Here we do not look at things from the y-axis. We look at things from the x-axis. And what we do is we divide the interval AB into subintervals. Now, you see here, you have here a typical subinterval from xi minus 1 to xi. You choose between, in this subinterval, a sample point, and it will turn out to be the best choice to use the midpoint in this case. We will see in a minute why. So we choose the midpoint, the sample point, and you approximate the area below the function f of x on the interval xi minus 1 xi and above the x-axis by the blue rectangle you see here. And now, instead of rotating the original area, what you do is you rotate this blue strip here. And what you get is it's a circular cylinder, but there is a hole drilled out in the middle. So-called, this is what we call a cylindrical shell. Okay. So you can approximate the blue solid, okay, as a sum of cylindrical shells, and you compute the volume of the cylindrical shells instead of computing the volume of the solid, and then let again n tend to infinity. And what you should get, and this is something you have to prove actually, what you should get should be the volume. Okay, you should be aware that you have to prove this. Okay, because we have defined the volume like this. Okay, and it's not so clear because this is a mathematical process here. Okay, limits and so on. So you have to prove they are the same. What you get is the same. But this is mathematically okay. For maybe in other classes, it's not so important to prove such things because it's clear. Okay, but if you want to be very precise, you have to prove it. We are not going to prove it because we do not spend too much time on such details, and it's not important for you because your major is not mathematics. Okay, so in order to use this method, what we have to figure out first is how to compute the volume of such a cylindrical shell. But of course, this is easy. And last time I showed you already the formula. Okay, so as a preliminary step, we have to figure out how to compute the volume of such a shell. Now what we have given is the height. Okay, and we have here two radius, inner and outer radius. So we have a radius R1, and we have a radius R2. Now, if we choose the radius which goes here to the middle, okay, so the average radius, which we call R, maybe a little bit too tiny, but okay, R is R1 plus R2 half. So the average radius, R1 is the inner radius, R2 is the outer radius. Then last time we saw already that a formula for the volume of the shell, easy to memorize, is the circumference of the circle with radius r times the thickness of the shell, so r2 minus r1 times the height. Okay, so this is a formula for the, as we have derived last time, is a formula for computing the volume of such a shell. And now, using this, you see, if you approximate the original solid by a sum of such shells, cylindrical shells, then the volume, okay, is approximated by, so you have to sum up over all those shells, the volumes of the shells. Now for the volumes of the shells, we have this formula here. Okay, so you have here 2 times pi times, and you see the average radius is, if you look at things like this, is exactly the midpoint of the ice interval. Okay, so this is this here. Now you have also a delta x times the height, and for the height we have to choose a sample point. Okay. Actually, we still have a choice, freedom for choosing the sample point, but you see that because this is f of some point. Okay, but you see, so here actually you have freedom. Okay, you can choose any point between the between xi minus 1 and xi, but what we want to have is that this is a Riemann sum here, and this is a Riemann sum in case where you choose the sample point to be the midpoint. Then everything is a Riemann sum. Okay, that's the reason why here for the sample point we choose the midpoint. Okay, so you see that the volume is approximated by this here, and if you take the limit as n tends to infinity, what you should get is the volume. So actually, this is something you have to prove. Okay, so the volume should be given by the limit n tends to infinity of the sum I from 1 to n 2 pi x f of x delta x. And you recognize, okay, because of our choice of the sample point, this here is the Riemann sum. So what we have here, by definition, is the integral from a to b 2 pi x f of x dx. Okay, and still, actually, there is this equality left, which you have to prove. But since you are not mathematic majors, we will drop this. We are not going to discuss these details. So you can say, okay. Using intuition, it's clear that they must be the same. So this is the formula which we obtain if we use this approach here, the approach by cylindrical shells. And this method is called method of cylindrical shells. See that this formula actually has a nice interpretation, so it's easy to memorize. There's nothing, actually, you do not have to memorize this process here, and also the formula you do not have to memorize, because this formula has a nice, easy interpretation. Namely, you can think about you fix here. So we look at things different, not from the y-axis. So we look now at things from the x-axis, and you see that, okay, you can look at things as follows. So you say, if this is the point x here, what you rotate is, so if this is the point x here, what you rotate is this orange line you see here. Okay, and you can think about this is something, this is also a cylindrical shell, but the thickness of the shell is 0, so very small. Now, if you let rotate this, okay, so if you take it here, if you open it and you roll it out, what you get is something like this here. So if you just take this piece here, then you get something like this here. Okay, so you get a rectangle, and you see that the sides of the rectangle are easy to obtain. So this is given by the height, and this one is the circumference of the base radius. Okay, and so essentially, and you sum up over all those areas, because the integral has the meaning of the sum here. So this is an easy way how you can memorize this formula, not a proof, but a nice way to memorize it. Because actually it's not a surprise that you have this kind of, once you prove this formula that you can interpret it like this, because it's kind of what we are doing already here, but here the shell still has a thickness, and in the limit process, okay, it's kind of, we look at the shell which still has a thickness, but the thickness is very small. Okay. So any questions to this? So actually there are two different methods how you can compute volumes. The first method, once more, is called the method of cross-sections. Second method is called the method of cylindrical shells. And it depends actually on the given solid where you have to compute the volume, which method to apply. Sometimes it's easier to use this method. Sometimes it's easier to use the other method. So you have to decide case by case. For instance, for this example, I stressed already. That's why I introduced this example. It's possible to compute the volume by our first method, but not very easy because you have to solve this for x. But it's much more easy to use this method here, because you see, using this method, the integral gets trivial. So using this method, the volume is the integral from 0 to 2, and then 2 times pi times x times the function. Okay, this is something which is trivial to compute. Okay. Now, let's maybe look at some of the examples we have considered last time, just to see how this method compares to the previous method. So last time we have looked at the following example. So our function was f of x is equal to e to the minus x. We considered the interval 0, 1. And again, we rotated this function about the y-axis. Okay, so you have here this area here, and assume we rotate it about the y-axis. Now, if we do this, okay, then our integral. So actually, we can write it down immediately. It's the integral from 0 to 1, 2 times pi times x times e to the minus x dx. I just want to recall that last time, using shells, okay, using cross sections, okay, we actually had to divide the problem into two subranges, but one subrange trivial. The other subrange, the integral which we encountered was ln x everything square. Okay, I told you we are not able yet, or we haven't discussed how to compute such an integral. Also, this integral here. The only method we have so far, I know some of you maybe have learned already the method, but the only method we have so far is guessing a solution. So if we look at this at this solid, it's not easier to use the method of cylindrical shells. So actually, using the method, if you use the method of cylindrical shells, you have to compute the integral x e to the minus x. If you use the other method, cross sections, what you have to compute is the integral ln x square. Okay, we will see today in the next section that the complexity of those integrals is about the same, because the method you can use is about the same. So here, for this solid, computing the volume, both methods do not work yet unless we know more about integration. Now, so let's maybe, because last time we also looked at the same problem, but we rotated the region about the x-axis. Okay, so maybe let's compare. If you use shells, okay, so how does this compare to the computation from last time? So again, you see, you have to divide. It's more complicated actually, because if you use cross sections, okay, you have as radius always e to the minus x, and the areas, the cross sections, you have to add up. Have area e to the minus 2x times pi, which is easy to compute. Now, if you rotate like this, you have, first of all, you have to divide the integral into two parts, but one part is actually easy because it's just a cylinder. The other part, you see, is the integral from this point to this point, so e to the minus 1 to 1, and then you have to integrate minus ln y times 2 pi dy. Okay, so you see, actually, this is an example where shells would be more complicated. Okay, because here you still have to handle this integral. We will learn in the next section how to do this. Okay, but if you use for this example cross sections, with cross sections you are immediately able to compute it. So this is an example where cross sections is better than cylindrical shells, and the example which I showed you, the cubic function, is an example where shells is better than cross sections. So it depends on the example, okay, which method you use. Okay, but we will see also this integral is not very complicated to compute. Okay, so this was one example from last time. Another example was two functions. We have f of x is equal to x squared, g of x is equal to the square root of x. And we look at the area which is enclosed by those two functions. Okay, so one function is this one. So this would be y is equal to x squared. The other function is this one. So this would be y is equal to square root of x. So what we have is this region here. And for instance, if we rotate it about the x-axis, okay, now using shells, okay, so normally if you use this method of shells, you can completely forget about the formula we derived today. You just use the interpretation I told you afterwards. So you see that, okay, so a typical line which is rotated looks like this here. So what you have to do is you have to integrate along the y-axis, so from 0 to 1, and then you have 2 times pi times y times, and then what you have to do is the length here of the red line. So what you have from square root of y is the larger one minus y squared dy. Okay, and you solve this, and you will get the same thing as last time. I hope I have I'm not going to spend time to solve something which is that trivial. Okay, so what you get is this here, as last time. Okay, so the only thing which is important here is actually not the formula from the textbook is important. Is the important thing. The remark below the formula is the important thing, namely to interpret the formula as, okay, you look at such red lines and you rotate the red lines. Okay, looking at things like this makes it much more easier to do the computations. You also see, for instance, if we rotate not about this line here but about another line, I'm not sure whether last time we have considered the case -1. Okay, so actually you can use almost the same. The only thing which changes is the radius. Okay, so for this case, the volume would be the integral again from 0 to 1, 2 times pi, and then the only thing which changes is the radius. You have to add here. So this here should be -1. You have to add here 1, but everything else is the same. Okay, and if you integrate this, it's also trivial to do this. So what you get is 29 over 30 times pi. Okay, but if you actually if you compare here which method is quicker, so either shells or cross sections, you will see it's about the same. Okay, almost the same. Okay, because it's also very easy here to solve this problem by using cross sections. So the only important thing is there are two methods. Okay, the method of cross sections and the method of cylindrical shells. And it depends on the example. Sometimes it's easier to use shells. Sometimes it's easier to use cross-sections. But there are also many examples where it's about the same. Okay? So using both of the methods work, and no one is preferable over the other one. We will go on to Chapter 7. And Chapter 7 discusses integration techniques. We have already seen that actually for the only thing we have to do is we have to take the laws for differentiation, or the techniques we have developed for differentiation, and try to inverse them. Now, we have seen this already for the sum rule. We have seen this already for the chain rule, which gives then the substitution rule. Now, one rule which is left is, okay, how to compute the product of the integral of a product. So in other words, how to reverse the product rule. Now, and here the problem starts. So if you once more recall the product rule, so this was the product rule. Now, if you want to reverse it, okay, so you take the integral. If you take the integral on the left-hand side, what you get is fg is equal to then the integral of the derivative of f times g plus the integral of f times the derivative of g. Okay, and you see this actually doesn't give you a formula which looks very helpful because, for instance, you can write it like this here. So whenever you have a product, okay, and you want to compute the integral, you see it's equal to f times g minus the integral f times the derivative of g. Now the unpleasant thing is here that, okay, actually you want to solve this, okay, but here the answer has still an integral, okay, so this is the unpleasant thing. Now, and this is the main reason why integration is more complicated than differentiation, because there is no equivalent to the product rule. Or in other words, it's not clear how to compute the integral of a product. Okay, there is just this rule which is called integration by parts, because you solve it. You solve the problem just partially. You still have the integral left. But the advantage of these methods in many cases is that the integral which appears here might be easier than the original one. And then you can use this method. And because it's not so clear sometimes for some examples, okay, whether the resulting integral is getting more easier. So this normally needs a little bit practice, but some of you maybe have learned it in high school. You have certainly seen it already in other classes. You need a little bit experience in order to use this rule here, but after you do a few exercises, not very complicated anymore. Now, maybe I should add here a dx, because sometimes this rule is also written in the form. So if you set u is equal to g of x and v is equal to f of x, then you see you can write this rule as the integral, and then u dv is equal to u minus the integral, and then you have v du. Okay, sometimes you see it in this form, but actually it doesn't make a lot of sense because this would be a new symbol for the integral. Okay, so this is just a rule to memorize this. It doesn't make any sense. Okay, so let's maybe look at some examples just to show you how this works. Now, we already saw, for instance, this integral here. Okay, we just encountered it. Now, in order to compute, normally, so you really have the integral of a product. You can use this kind of product rule. But the first thing you have freedom in order to choose the derivative of one function, and one function is g of x. So you have freedom how to choose them, because their role is not the same. Now, you see that one function you will afterwards take the derivative. One function you have to integrate. So you have to make sure that the function which you choose here, the function which you choose to be f, that you are able to integrate it. And you have to make sure that this is getting more easy. Now, since if you choose this to be equal to g, since the derivative of this function is much more easier than the original function, it is likely that this method is going to work. So what we do is we choose the derivative of f to be equal to e to the minus x, and g of x to be equal to x. So here the integral is easy to compute. It's minus e to the minus x. And here the derivative is getting more easy. Now, you see, okay, this is equal to minus x e to the minus x minus, and now you have the integral over the product of those two, so you have here plus e to the minus x dx. And indeed, this integral is more easy than the original one. So using this method for this example is successful. So here, minus x e to the minus x minus e to the minus x, actually plus a constant. So you have e to the minus x, maybe a minus x plus 1 plus a constant. Okay, so this is one example where this works. So you see that there are several, for students who do this the first time, unless you have seen already many examples. If you have seen already many examples, there is no difficulty in doing this here. So all those examples are just interesting if you see them for the first time. Otherwise, they're not interesting anymore. But if you see them for the first time, most of them would be quite challenging, good exercises to train your problem-solving skills. But if you have seen them already, then it's useless. You see another integral which can be handled by this method. Another important case is ln of x. Okay, here the only problem is that you see, okay, actually not a product, but this is easy to make into a product. So you have 1 times ln of x. Okay, now you observe something that if you have the ln of x, if you take the derivative, what you get is 1 over x, which is somehow much more easy than ln of x. So whenever you have here in this case, you will choose the role of f and g quite differently. Here you chose g such that the derivative is more easy. Okay, you will do the same here. But here, if you choose this as the derivative of f of x, will be more complicated. But we see, okay, it's still the integral which appears on the right-hand side is manageable. So we choose the derivative of f to be 1, which means that f of x is equal to x. And we choose g of x to be equal to ln of x, which means that the derivative of g of x is equal to 1 over x. Okay, then this becomes here x times ln of x minus the integral of the product of those two, which is getting very easy, namely 1. That's why this works. And you see that because this integral is equal to x, so this is the answer, as we have already seen several times. So you can use this method in order to integrate this function here. Now, another function we have encountered last time is this one. Okay, also this function, not complicated to integrate. Actually, here you have already several choices. You could choose the derivative of f of x to be equal to ln of x, but then the integral is getting rather complicated. Okay, you can choose both of them, ln of x, but then here this part would be rather complicated. This would be easy. Doesn't look very successful. So it looks much better to use this here. Okay, to use the same idea. So write 1. Then again you choose the derivative of f of x to be equal to 1. So the integral will be equal to x, and you choose g of x to be equal to ln x squared. Then the derivative is equal to 2 ln x times 1 over x. Okay, and then you see, okay, so our integral ln x squared dx becomes x times ln x squared minus the integral of the product of those two, and this one is manageable because we solved it already. Okay, so you see this is x times ln x squared minus 2 ln x plus 2x plus a constant. You see, the more integrals you have solved, the easier it becomes. Okay, because you can just try to, whenever you can find the choice of those two functions such that the integral here is one you already know, then you are finished. Okay, so this is another example. So now, using this example, we would be able to compute the volume of the solids if we take e to the minus x and rotate it about the y-axis from 0 to 1. Because essentially what we get is such a, using cross sections, what we get is this integral here. This one. Okay, also this easy. And so in this case, you will take the derivative of f of x is equal to x. So f of x will be equal to x squared half, and g of x will be equal to ln of x. The reason why you choose g of x to be equal to ln of x, because the derivative is more easy. Okay, so what you get is this is equal to x squared half ln of x minus the integral. And the remaining integral, so you take out 1/2, it's very easy. Okay, so what you get is x squared half ln of x minus x squared over 4 plus a constant. Okay, so also, so you see, whenever you have something like, whenever you see a ln of x, it might be a good choice to choose the ln of x to be equal to the g of x. Not necessarily, but might be. Because you see, in this case, we also choose here, in this case, we choose the x here to be the function to be integrated, okay? But if ln of x is replaced by e to the x, okay, we do it differently. We choose the functions the other way around. Because in many cases, actually differentiating a polynomial would make it easier, because the degree, you get a polynomial with a degree which is 1 less the original degree. But in this case, it's the other way around. The method becomes successful. Okay, so you just do the same. You again 1 times. Okay, now the function which you integrate is the 1. The function which you differentiate will be the arctangent, because the reason is more or less the same as here. If you differentiate ln of x, a complicated function will become much more easier. It will become a rational function. Here the same. Okay, so you see that the derivative. Okay, and here the integral is equal to x. Now you see that, okay, so this is equal to x times the arctangent of x minus, and then you have here the integral x over 1 plus x squared dx. And this integral looks much better than the original one. In particular, you can substitute here, because you see that the inner derivative of this function here is there as a factor. So if you substitute u is equal to 1 plus x squared, you see that du becomes 2x dx. So everything becomes the x times arctangent of x minus, so you have here a 1/2, and then the integral is just 1 over u du. Okay, so what you get is x times the arctangent of x minus 1/2 ln absolute value of u, which is 1 plus x squared. Because this is always positive, you can drop the absolute value plus the constant. Okay, so the same trick. I guess some of you, maybe most of you, have already seen this, or some of you, and I don't know. If you have seen this, this just makes fun. This is just something which is interesting to do if you haven't seen it. If you have seen it already, if someone told you, okay, then there is no joy in doing it anymore, because then you just repeat what other people told you. Now, another standard example. Maybe some of you have seen it before. Would be this one. For instance, let's choose to differentiate sine of x and integrate e of x. So the derivative of f of x should be equal to e of x, which means f of x is equal to e of x, and g of x is equal to sine of x, which means the derivative of g of x is equal to cosine of x. Now this means that the integral is equal to e to the x sine of x minus the integral e to the x cosine of x dx. But obviously this integral is not easier than the original one. It's about the same complexity. So what we do here, and this is the trick which you have to see once, namely you just use the same method in order to handle this here. So what you do is, okay, again, of course we will not change the order here, otherwise we are back to the original one and we prove nothing. Again, we are going to integrate e to the x, and we are going to differentiate the cosine of x. So the derivative will be equal to minus sine of x. So this is then equal to e to the x sine x minus now e to the x cosine of x. And you have here 3 minus, so you have a minus e to the x sine of x dx. Okay, so what is the gain of this? You see that now you have a relation which tells you that this integral here, okay, is equal to this part here minus this one. So you put it on the other side and divide everything by 2, and you get the integral. Okay, so you see that the integral e to the x sine of x dx is equal to, you can take out e to the x, e to the x half sine of x minus cosine of x plus a constant. Okay, so you see that you are lucky here, okay, because doing things twice, you will be back to the original integral, and you have a minus here. So you just take it, this as an identity, and solve it for this for the integral here. Okay. So this is a trick you have to see once, and then you can apply it to many other situations, because this is a trick which will work for many other integrals. We will see this in a few minutes. Now, if you introduce here boundaries, okay, so if you have a lower and upper limit, you have the same rule. You have just to evaluate this part here. So you have the same rule as this one. You just have to evaluate this part here, the boundaries, and you have to keep the boundaries here. That's the only thing you have to do. So you have a similar method, integration by part, for definite integrals. You have a similar formula for the definite integral. Minus integral a to b f of x, derivative of g of x dx. Same formula. The only thing you have to do is you have to evaluate this part here, upper and lower limit, and you have to keep the limits here. So that's the only thing which is different. Now, maybe let's look at an example. So if you look at the integral of sine of x dx, this is like very easy. So minus cosine plus a constant. Okay, if you look at the integral sine square of x dx, okay, so you maybe have seen that there is a trick in order to compute this integral here. Now, the most easiest way, you could use partial integration. So you integrate the sine, differentiate and differentiate the sine. This is one method, but maybe you have seen that the most easiest method is to use the half-angle formulas. Okay, if you do this, you can take out 1/2, and the rest is x minus the integral cosine of 2x dx. Okay, and here actually you have to use substitution. Okay, so you have this is equal to x half minus, and here you have sine 2x half, and from this 1/2 over 4 plus a constant. Okay, so maybe some of you have seen this kind of trick. Okay, there are many different ways to compute this integral here. One way would be integration by parts using the method we just have seen, but this is maybe more quicker, so you use the half-angle formulas. Now, but what I have in mind is, okay, so we see the integral of the sine is this, the integral of sine square is this, Now, the next question would be, okay, sine to the cube, sine to the 4, sine to the 5, and so on. So let's compute already sine to the n. Okay, so let's look at the integral sine of x to the n, where n is any possible power larger or equal than 1. Now, in this case, obviously this will not work here. Okay, so we use our method of integration by parts. So we look at, okay, so let's say we take out one sine, we integrate one sine, okay, and differentiate the rest. The rest is sine of x to the n minus 1. Okay, so if you integrate this, you see f of x is equal to minus the cosine of x. And here the derivative is n minus 1 times the sine of n minus 2x. And we have from the inner derivative the cosine of x. Okay. Okay, so this reduces the problem to, okay, so we have minus the cosine sine to the n minus 1x, and then we have plus n minus 1, and then the remaining part is the integral cosine square of x sine to the n minus 2x dx. Okay. Now we rewrite the cosine. So here, it's good to switch back to the sine. So the cosine square of x is 1 minus sine square of x. Okay. Now if you do this, what you get is this is equal to minus the cosine. Sorry, here I forgot the x. Cosine of x sine to the n minus 1 x plus n minus 1. So one integral is the integral from over sine of x to the n minus 2 dx. Okay, and you have a minus n minus 1, and then you have the integral, and this is if you plug this in, what you get is the sine to the nx dx. Now, what do we have gained from this? So again, you look at everything, the whole equation. Okay, and what you want to compute is this here. Okay, so you put it on the other side and divide everything by n, and you get the following formula. Okay, so you get the following formula. The integral sine n of x dx is equal to minus cosine of x sine of x to the n minus 1 plus, and I have here, sorry, minus 1 over n, and I have here n minus 1 over n, and then the integral sine of x to the n minus 2 dx. If n is equal to 2, okay, then here what you get is 0 as exponent, so this is then 1, and you can compute this integral. Okay, so for n is equal to 2, you can use this in order to compute the integral. Now, for n is equal to 4, okay, you get here n is equal to 2, and you can plug in what you have already computed. So you can use this here recursively in order to compute this integral here for all powers of n. Okay, you just reduce it to previous cases. Okay, so this is a little bit similar to you remember we had previously a homework example where you had to compute some limit without using the L'Hopital, and it was similar method. So you use this kind of recursion. Okay, so you see here this relates this integral to the same integral, but the power is reduced. Okay, so if n is even, okay, you will eventually, if you repeat this, you will end up with something which is 0 here, and if n is odd, you will end up with something which is 1 here, and both integrals you can easily handle them. Now I will use this and show you a nice application of this result. Because I haven't talked about definite integrals yet, so this is not a definite, this is indefinite integral. So you have here the integral 0 to pi half sine to the n of x dx. Okay, if you choose this special case, you see that because you have to evaluate this at pi half and 0, at pi half the cosine is equal to 0, at 0 the sine is equal to 0, so this will drop out. And what you get is okay, this is actually interesting because now look at this here. So let's look first at the case where n is even. Okay, so let's say we look at this case here. Okay, so you just use what I have proved here. So you have 2n, then you have here 2n minus 1, and then you end up with the integral from 0 to pi half, and then you have the sine of 2n minus 2 x dx. Okay, now you repeat this, okay, once more. So you get 2n minus 1 over 2n, okay, and here from here you get 2n minus 2 over 2n minus 3, and then the integral from 0 to pi half, the sine of 2n minus 4 dx. And you go on like this. Okay, now what do you get? So you see that in the denominator you will get many numbers, okay, but in the denominator you start with 2n, the next one is 2n minus 2, the next one will be 2n minus 4, and you go on like this. The last one will be 2. And in the numerator what you have is 2n minus 1, then the next one is 2n minus 3, and you go on like this. Then you have one is 3, and the last one here will be 1. Okay, and here, if you have here 2 and here 1, if you look at this here, then the power would be equal to 0. So what you get here is x. So what you get here, pi half. Okay. Now we do the same for the odd. Maybe I shouldn't erase this. I just write this here. Now let's look at the odd one. So if you look at the case where the exponent here with which you start is odd, then you have here, let's say for instance 2n plus 1. Actually, if you plug in once, you get something which is similar. So you have here 2n plus 1. Okay, you see this is the denominator. You have 2n in the numerator. And then the integral goes from 0 to pi half, and then you have a sine of 2n minus 1 x dx. And you repeat this. Okay, if you repeat this, what you get is, okay, if you do this once more, you see the numerator is getting 2n minus 1, and the denominator will get 2n minus 2. Okay, and you reduce here the order again by 2. Okay, now if you keep on doing this, okay, so you see that for the last one, okay, so you will end here up with 2. You will here have a 3. Okay, and then so in this case n is equal to 1. So you see that what you have here is the integral from 0 to pi half, and then sine of x dx. Okay, but this here will be minus the cosine of x evaluated at 0 and pi half. At the upper limit is equal to 0, at the lower limit is equal to 1. So this is 1 here. Okay. Okay, so let's maybe also this is interesting because this means, okay, what you get here. So this expression here, something similar, but now you start here in the in the numerator with 2n plus 1, and the next one is 2n minus 1, and you go on like this here, and the last one was 3, so 5 times 3, and what you get in the numerator is 2n minus 2, and the last two are 4 and 2. So in the denominator, all odd numbers. In the numerator, all even numbers. Okay, now let's define the integral from 0 to pi half sine to the nx dx. So let's call this integral here in. Okay. Now what you see is, because in this range here the sign is positive, smaller or equal than 1. Okay. So if you replace n by n plus 1, okay, you will make this even smaller. Okay. So this is certainly larger than. Okay. So this sequence here is decreasing. Okay, now look at this. This is now something very pretty will come out from this. Okay, so if you look at this here, okay, and you look at this expression here, okay, so you see that actually, if you look at this number I2n plus 2, it's almost the same, okay, as this one, but here you have two numbers more, okay, at the front. Okay, so you see that this one here is 2n plus 2 over 2n plus 1 times I2n. Okay, because if you go from 2n to 2n plus 2, the only thing you do here, you add two numbers at the beginning over I2n. Okay. Now you see that this here is smaller or equal than, because this sequence is decreasing, so smaller or equal than I2n plus 1 over I2n. Okay. But again, because this is decreasing, so it's smaller than I2n over I2n. Okay, but this is equal to 1 here. Okay, so we have shown that I2n plus 1 over I2n is smaller or equal than 1 and larger or equal than, here you can cancel this, 2n plus 1 over 2n plus 2. Okay, now you let n tend to infinity. If n tends to infinity here, this will go to 1. This will go to 1 as well. Okay, so this will go to 1 by the squeezing theorem. So we see that this here will go to 1. Okay, and now the only thing you have to do is you have to write this out. Then what you get is something very pretty. Okay, so we have just proved that this here tends to 1. Okay, so we have just proved that the limit n tends to infinity I2n plus 1 over I2n goes to 1. Now, if you write this out, what do you have? You see that I2n plus 1 over I2n, okay, is equal to. So you must divide this by this here, okay. So you see that you have in the numerator you have all the even numbers twice, okay. So you have here 2n square, then you have 2n minus 2 square, and so on, times 4 square times 2 square. And if you look in the denominator, you have all, more or less all odd numbers twice. Actually, you have one more here. So you have 2n plus 1. Then you have 2n minus 1 square, and you go on like this, and you have 5 square and this 3 square. Okay, and we have also a 2 over pi. Okay, and as n tends to infinity, this will go to 1. Or in other words, now you have the following pretty formula. Okay, so in the numerator you have all even numbers twice. In the denominator, all odd numbers twice. So you have here 2 times 4 times 4 times 6 times 6 times 8 times 8 and so on, over 3 times 3 times 5 times 5 times 7 times 7 times 9 times 9 and so on. So if you compute this, what you get is pi half. Now this is something which was discovered already a long time ago. So this is what we call in mathematics Wallis product. This was discovered by a guy which is called Wallis, a mathematician. I think Wallis discovered this already in the 17th century. Now, this was certainly not because this is quite easy. It's not so complicated. If you know a few tools about integration, a few methods about integration, you can prove it, as I have shown you. The more surprising fact is that when Wallis lived, the integration was not invented yet. Okay, so he proved this without the theory of integration. Even more surprising, when Wallis lived, the limit was not clearly defined yet. So Wallis himself certainly used a completely other method to deduce this famous result here. You have to notice the symmetry. All the numbers which are involved here are integers, but what you get is a number which is transcendental, a number which is irrational. It's quite surprising. Okay, so any questions to this? As I said, this is a couple of exercises at the end of section 2.1, and I combined them all and showed you this method because this is a famous result. Maybe you have seen it already before, and the proof actually is not. Also looks quite complicated, but the proof is not too complicated once you know something about integration. Actually, because we have discovered that there is no analog of or no good analog of a product rule. So whenever we have the integral of a product, we run into kind of problems because we do not have a formula which tells us what is the result. We just have the integration by part, where we need which might work in some cases but not work in others. And as I have already stressed, this essentially is the main complication of integration. So integration will, because of this fact, will be slightly more complicated than integration. Now, what we will do in the next sections is we will just look at classes of functions, like rational functions, and we will discuss systematically how to compute the integral of certain classes of functions. The first class of function we have to consider are trigonometric functions. So essentially, we will look at integrals where the integrand is some combination of trigonometric functions. So for instance, let's start to discuss integrals of this type here. Okay, so first we are interested in how to solve integral of this type here where n and m are non-negative integers, any non-negative integers. Okay, now, so first let's maybe look at some examples. So let's maybe look at this example here. Now, some important fact you easily observe here is that the derivative of the this is not a good example. Let's maybe look at this one. Okay, so something which you observe here is that the derivative of the cosine is equal to the sine is equal to minus sine, and the derivative of sine is equal to cosine. Moreover, we know that sine square plus cosine square is equal to 1. Okay, so this is essentially what we will need. So the derivative of sine of x, the cosine of x, the derivative of the cosine of x minus the sine of x, and sine square of x plus cosine square of x is equal to 1. This seems to be helpful because you see, if you take out here one sine, what remains is sine square of x. And you can use this in order to replace it by cosine. And then you will substitute u is equal to cosine of x. Okay, so if you want to solve this integral, now what remains is sine square of x, but sine square of x is 1 minus cosine square of x. So you see what remains is something in cosine, okay? And now what you do is, okay, you will make this substitution here, because the derivative, you see it here as a multiplicative factor, so everything will become minus the integral 1 minus u square, and you have a du. Okay, and this is easy to solve. Once we encounter an integral which is easy to solve, I'm not going on because it's a waste of time. Okay, so this is easy to solve here. So you see, but we have to think, okay, for which situations? For instance, if we take out one cosine, this wouldn't work, okay, because if we take out one cosine, there is only one cosine left, and we cannot replace it by sine, okay, unless actually we can do it, but we have two solutions and so on. Okay, so but if you look at the cosine, this doesn't work so well because this identity, okay, you do not have it. Now, so this will work if the power of sine is odd, okay? Because then if the power of sine is odd, you can take out one sine, the power of the rest is even. And if the power of the rest is even, okay, you can use this in order to transfer it to cosines. Okay, so whenever you have such an integral, okay, and the power of n is odd, what you do is you take out a sine, and then you have sine of x to an even power, and you use this in order to replace it by cosine, and then you make this substitution. So this will work whenever n is odd. Here for m, even it's not necessary that the second. It's not necessary that the second function is of this form here. Okay, even if this is the square root of cosine of x, you can still use this method. For instance, if you have here the square root of cosine of x, you can still use this here because then here you have a square root of x. Okay, but it doesn't matter. So we observe once more, if n is odd, it's an odd number, we can always take out one sine, replace the rest by cosine, and make the substitution u is equal to cosine of x. Now, if m is odd, the same, because symmetry. Okay, so the only case which is left is n and m are both even. Okay, so this is the only case which is left. And if n and m are both even, what you use half-angle formulas, as we have seen before. Okay, so you can use the half-angle formulas in order to replace the even n by n half. Okay, and then again, you look whether they are odd or whether both are even. Again, half-angle formula, and so on and so forth. Okay, so this class of functions is completely trivial for us to integrate. Okay, maybe I show you, just to make this complete. I show you the general case. Okay, so let's assume. So assume n is odd. Okay, so this means n is equal to 2k plus 1. Okay, then the integral is the integral sine of 2k plus 1 x cosine to the mx dx. Now, in this case, what you do is you take out the sine, okay, and the rest is then sine of 2, sine to the 2k, but sine square you can replace by 1 minus cosine square of x to the k cosine x to the n dx. And now you substitute u to be equal to cosine of x. Okay, then what you get is minus, just the same as what I have erased, minus the integral 1 minus u squared to the k u to the m du. And this is manageable because it's just a polynomial. Okay, so if this exponent is odd, this works. And of course, similar if m is odd. Now, So as I have explained, what is left is both exponents are even. So for instance, if you have the integral cosine to the fourth x dx, okay, in this case you cannot apply this because both exponents are even. One is 0, is an even number. One is 4. Now in this case, but in this case you can replace the power of 4 by 2 if you use the half angle formula. So you have here 1 plus cosine of 2x half square dx. Okay. Now this is 1 over 4, and you have to integrate this out here. So you have 1 plus 2. You have to multiply this out. So you have 1 plus 2 times the cosine of x plus the cosine of 2x square dx. And this is now not complicated to compute. So this is 1 over 4x plus, and actually here you have to use the substitution rule. So, but this is now minus plus sine of 2x, cosine of 2x, then a 2 out over 4, plus 1 over 4, the integral cosine of 2x square dx. Now actually here you can replace 2x by u. So we have, so 2 dx is equal to du. So what you have here is 1 over 8. For this here, you just use the same trick. So once more, half angle formula. 4 plus x over, actually this is u, and u is equal to 2x. So you have here this over 8. Plus, and here you have again the sine of 2u. So if you, this is the cosine of 2u times 2, so 32. And u is equal to 2x, so it's 4x plus the constant. Okay, unless I have made a computation error. But the important thing is, okay, that if you use the trick with the half angle formula, you can reduce the power here by 1/2. Okay, so 4 will become 2. Okay, and then you can use the trick once more, and 2 will become 1. But if it is 6, okay, then you use once the half angle formula, you will end up with 3, and then you have the odd power. Then you can use the substitution I explained before. Okay, so you see that now all cases, okay, are covered by all such integrals are covered by 3 situations. The first situation is that the power of the sine is odd. Okay, then you take out the sine, rewrite the rest in terms of cosine, and substitute u is equal to cosine of x. The second situation, which is symmetric to the first one, is the power of the cosine is odd. Then the third situation, which is left, is both exponents are even. Okay, and if both exponents are even, you just use the half angle formulas.